Look up at the night sky on a clear evening, and you might spot the constellation Leo, a familiar pattern of stars that has guided travelers for thousands of years. But beyond what the naked eye can see lies something far more mysterious: the Leo cluster, a sprawling collection of galaxies so vast it defies comprehension. This isn't just another patch of space, it's a cosmic playground where the rules of physics seem to bend, where unexplained phenomena lurk in the shadows of the universe. Strange bursts of energy, galaxies moving in ways they shouldn't, even whispers of something invisible tugging at the fabric of reality. These are just a few of the enigmas hiding within the Leo cluster. Imagine a place where entire galaxies dance to an unseen rhythm, where light itself behaves in ways that leave scientists scratching their heads. The Leo cluster isn't just a distant curiosity, it's a puzzle that challenges everything we think we know about the cosmos. Some of these mysteries might hold the keys to understanding dark matter, the elusive substance that makes up most of the universe. Others could point to forces we've yet to discover, forces that rewrite the textbooks. And then there are the phenomena so bizarre, so utterly inexplicable that they seem to defy explanation entirely. This is where our journey begins. Over the next few minutes, we're diving deep into the heart of the Leo cluster, exploring 25 of its most baffling, awe-inspiring mysteries. From ghostly radio waves to galaxies that vanish without a trace, each one is a story waiting to be told. Some might send chills down your spine, others will leave you in sheer wonder. But one thing's for certain: by the time we're done, you'll never look at the night sky the same way again. So buckle up, the universe is about to get a whole lot stranger. One of the most unsettling mysteries in the Leo cluster involves a galaxy that simply vanished. Astronomers first catalogued it decades ago, a faint but unmistakable swirl of stars nestled among its celestial neighbors. Then, without warning, it disappeared from telescopic observations. No explosion, no trail of debris, just an empty patch of sky where a galaxy once thrived. What could make an entire galaxy vanish? One leading theory points to dark matter, the invisible scaffolding of the universe. If a dense knot of dark matter passed through this galaxy, its gravitational pull might have torn stars apart so violently that they scattered into the void, leaving no visible trace. Another possibility is that the galaxy collapsed inward, swallowed by a supermassive black hole so efficient that not even light escaped its grasp. But here's what really stumps scientists: even these explanations don't fully add up. Dark matter interactions should leave some detectable disturbance in nearby galaxies, yet the surrounding cosmic neighborhood remains eerily undisturbed. And while black holes are voracious, they typically announce their meals with bursts of radiation, yet this disappearance was utterly silent. The case of the vanishing galaxy challenges our understanding of how galaxies live and die. It's like a detective story where all the clues point to impossible conclusions. Could there be forces at work we haven't even imagined, or is the universe playing tricks on us, hiding something in plain sight? Whatever the truth, this cosmic ghost story reminds us that even the most familiar corners of space can still hold jaw-dropping surprises. Deep within the Leo cluster, astronomers have picked up something that shouldn't exist: a series of powerful radio bursts repeating in a pattern that defies all logic. These aren't your typical cosmic blips. They pulse with such precision and energy that they've sparked debates stretching from scientific conferences to late-night conspiracy forums. The signals arrive like clockwork, then vanish for months, only to return with a cryptic intensity that leaves researchers scrambling for answers. One leading theory points to magnetars, super-dense, highly magnetized neutron stars spinning at dizzying speeds. When these cosmic powerhouses experience starquakes, their crusts can crack, releasing bursts of energy so intense they ripple across the universe. But here's the catch: the bursts from the Leo cluster don't match the usual fingerprints of magnetar activity. They're too regular, too clean, almost as if they're engineered. This has led some to propose an even more radical idea. Could these be signals from an advanced civilization? The notion isn't as far-fetched as it sounds. Scientists working with SETI, the search for extraterrestrial intelligence, have long speculated that an alien society might use focused radio beams as cosmic lighthouses. The erratic timing of these bursts could be intentional, a way to conserve energy or avoid detection by natural cosmic interference. Yet skeptics counter with another possibility. What if we're witnessing an entirely new astrophysical phenomenon? The Leo cluster is packed with galaxies, black holes, and turbulent magnetic fields, a perfect laboratory for behaviors we've never seen before. Some researchers suggest these bursts might be the echoes of collapsing wormholes or the remnants of ancient cosmic collisions, reverberating across billions of years. Whatever the truth, these enigmatic signals force us to confront just how little we truly understand about the universe. They tease us with their rhythm, daring us to decipher their origins. Are they the heartbeat of a dying star, the greeting of a distant intelligence, or something even stranger? For now, the Leo cluster keeps its secrets, but with every new burst, the mystery only deepens. The Leo cluster holds one of the most puzzling secrets in modern astrophysics: dark matter behaving in ways that shatter our expectations. Normally, dark matter forms an invisible halo around galaxies, providing the gravitational glue that holds them together. But here, observations reveal something far stranger. The dark matter isn't distributed evenly. It clumps in bizarre, uneven patterns, as if some unseen hand sculpted it into shapes our theories can't explain. Gravitational lensing, the bending of light around massive objects, gives us our clearest window into this mystery. When astronomers study how light from distant galaxies warps as it passes through the Leo cluster, they've found distortions that shouldn't exist. Some regions deflect light far more than the visible matter suggests, implying hidden concentrations of dark matter. Other areas appear almost empty, as if the dark matter has been scooped out. It's like mapping the outline of a shadow, only to realize the shadow itself has holes. One leading hypothesis suggests that dark matter might interact with itself in ways we don't yet understand. Most models assume it passes through other particles ghost-like, without collisions. But what if certain regions of the Leo cluster contain dark matter that does interact, clumping or scattering in unexpected ways? This could explain the patchy distribution, like a cosmic game of bumper cars where only some players feel the collisions. Then there's the spine-chilling alternative. We might be seeing the fingerprints of an entirely new force. Dark matter is already mysterious, but if some unknown influence is actively rearranging it, our entire framework for cosmic structure could need rewriting. The implications would ripple far beyond this single cluster, forcing us to rethink how galaxies form and evolve across the universe. Every new observation deepens the intrigue. The Leo cluster's dark matter doesn't just defy our models, it taunts them, presenting a puzzle with pieces that refuse to fit. Is this a quirk of nature we've yet to decode, or evidence of physics operating in ways we've never dreamed? One thing's certain: the answers, when they come, could reshape our understanding of reality itself. Among the constellation of mysteries in the Leo cluster, few are as baffling as the eerie gamma-ray glow that suffuses its galaxies. This isn't the usual flickering of distant stars or the predictable hum of cosmic radiation. It's an enigmatic, persistent light show, bathing the cluster in high-energy photons that shouldn't exist in such abundance. Picture a fog of invisible fire, radiating energies millions of times more powerful than visible light, yet its source remains stubbornly hidden from our telescopes. The first clue lies in the distribution of these gamma rays. Unlike typical emissions which spike around known objects like pulsars or black holes, this glow is diffuse, almost uniform, as if the entire cluster is submerged in an ocean of radiant energy. One explanation points to cosmic rays, high-speed protons, and atomic nuclei colliding with interstellar gas. When these particles smash into hydrogen atoms, they can produce gamma rays as a byproduct. But here's the problem. The observed intensity far exceeds what such collisions should generate. It's like hearing a whisper turn into a scream without anyone raising their voice. Then there's the more tantalizing possibility: exotic particle decay. Theories like supersymmetry suggest the universe might contain particles we've never detected, relics from the Big Bang that slowly disintegrate, releasing gamma rays as they vanish. If true, the Leo cluster could be a graveyard for these phantom particles, their final breaths illuminating the cosmos. Yet even this elegant idea stumbles when faced with the data. The glow's intensity varies in ways that don't align neatly with predicted decay patterns, leaving scientists to wonder if they're missing a crucial piece of physics. And then there's the wild card. Could this be evidence of dark matter annihilation? Some models propose that when dark matter particles collide, they annihilate in bursts of gamma radiation. The Leo cluster, with its dense pockets of dark matter, would be the perfect stage for such a spectacle. But if that's the case, why doesn't the glow match the expected distribution of dark matter in the cluster? The mismatch is like finding footprints that lead nowhere, a trail that vanishes just as the hunt gets interesting. What makes this gamma ray glow so unnerving is its refusal to fit neatly into any box. It taunts us with possibilities, each more thrilling than the last, yet steadfastly resists confirmation. Is it the aftermath of countless unseen collisions, the death throes of unknown particles, or something even more extraordinary? For now, the Leo cluster keeps its secrets glowing faintly in the dark, a cosmic riddle written in light we're only beginning to decipher. In the heart of the Leo cluster, where galaxies jostle like crowded city lights, there's a place where the cosmos goes silent, a vast, empty expanse astronomers call the Leo void. Picture a bubble in the universe over 300 million light-years wide, where galaxies should thrive but don't. It's not just sparsely populated, it's unnervingly barren, as if someone carved a hole in the fabric of space itself. Voids like this exist elsewhere in the universe, but the Leo void is different. Most cosmic voids are the natural result of gravity pulling matter into dense filaments, leaving empty pockets between them. Yet the Leo void's sheer scale and razor-sharp edges defy expectations. It's too large, too clean, like a cosmic vacuum swept through and left nothing behind. Even stranger, galaxies at its borders appear unnaturally aligned, as if pushed aside by some invisible force. One theory suggests the void might be the aftermath of a cataclysmic event, like the collision of two superclusters that flung matter outward, leaving a vacuum in their wake. Another idea points to dark energy, the mysterious force accelerating the universe's expansion, which could have stretched this region thin over billions of years. But neither explanation fully accounts for the void's startling emptiness. If dark energy were responsible, why don't we see other voids of this scale? And if a collision created it, where's the debris? Then there's the spine-tingling possibility that the Leo void isn't empty at all, but filled with something we can't see. Could it be packed with dark matter so cold and diffuse that it evades detection, or harboring rogue black holes that devoured every galaxy that wandered in? Some even speculate about exotic physics, like a patch of space where the laws of gravity operate differently, preventing galaxies from forming altogether. What makes the Leo void truly humbling is how it exposes the gaps in our cosmic blueprints. Simulations of the universe's evolution struggle to recreate such extreme voids, suggesting our models might be missing a critical ingredient. Is this a fluke of nature or a clue to something far grander? For now, it stands as a silent enigma, a reminder that even in the busiest corners of the cosmos, emptiness can be the most profound mystery of all. Imagine a planet with no sunrise, no sunset, just endless darkness as it drifts alone through the void. These are the rogue planets of the Leo cluster, celestial nomads untethered from any star. Unlike Earth, which basks in the warmth of the sun, these worlds wander the cosmos in perpetual night, their existence defying everything we thought we knew about how planets form and survive. Most planets are born in the dusty disks around young stars, but rogue planets tell a different story. Some may have been violently ejected from their home systems by gravitational clashes with neighboring worlds, a cosmic game of pinball where the losers are flung into interstellar space. Others might have formed in isolation, collapsing directly from dense clouds of gas and dust without ever orbiting a star. The Leo cluster, with its crowded galaxies and turbulent gravitational forces, is the perfect breeding ground for such orphans. What's truly astonishing is how these starless worlds endure. Without a star's heat, their surfaces should be frozen wastelands, yet some might harbor hidden oceans beneath miles of ice, kept liquid by the crushing pressure of their own gravity or the lingering warmth of radioactive decay. Others could have thick atmospheres trapping geothermal heat, creating pockets where against all odds life might cling to existence. Scientists even speculate about exotic energy sources, like tidal forces from passing stars or the slow burn of residual formation heat, keeping these planets active far longer than expected. But the real enigma lies in their detection. Rogue planets emit almost no light, making them nearly invisible to traditional telescopes. Astronomers hunt them using microlensing, a technique where the planet's gravity bends light from distant stars like a magnifying glass, betraying its presence for just a fleeting moment. In the Leo cluster, where countless such worlds may lurk, each detection feels like catching a ghost. The existence of these solitary wanderers forces us to rethink the boundaries of habitability. If life can persist in the cold, starless depths of space, where else might it hide? The rogue planets of the Leo cluster are more than cosmic curiosities, they're testaments to the universe's relentless creativity, proving that even in the harshest corners of existence, the unexpected finds a way. At the edge of the Leo cluster, a quasar flickers like a dying light bulb, except this isn't just any cosmic beacon. It's a supermassive black hole feeding on gas and dust, typically one of the brightest objects in the universe, yet its light fluctuates wildly, dimming and flaring in patterns that leave astronomers utterly stumped. Most quasars pulse with a rough predictability, their brightness tied to the ebb and flow of material spiraling into their black holes, but this one, it dances to its own chaotic rhythm, defying every known rule of black hole behavior. The strangeness starts with the timescale. Typical quasars brighten or fade over months or years as their accretion disks, the swirling rings of doomed matter, expand or contract. This one, however, can plunge into darkness in mere hours, only to roar back to full brilliance days later. It's as if someone's flicking a cosmic switch at random, turning the quasar's energy tap on and off with no regard for physics. One moment, it's a blazing lighthouse, the next, it's barely an ember. Scientists have scrambled for explanations. Could a thick, clumpy disk of debris be passing between us and the quasar, casting temporary shadows? Maybe, but the shadows would need to move impossibly fast, requiring structures larger than entire solar systems to zip around at near light speed. Another theory suggests a second, smaller black hole might be orbiting the primary one, its gravity yanking the accretion disk like a cosmic yo-yo. Yet even this elegant idea falls short when faced with the sheer violence of the brightness swings. The energy required would rip most disks apart long before they could flicker so dramatically. Then there's the spine-tingling third option. We might be witnessing a black hole in the act of breaking physics. Some models of quantum gravity predict that spacetime itself could froth and churn near a black hole's event horizon, creating microscopic tunnels or wrinkles that sporadically block light. If true, the quasar's flickering could be our first glimpse of a realm where Einstein's rules bend or shatter entirely. What makes this flickering enigma so thrilling is its defiance. It refuses to fit the mold, taunting us with behavior that should be impossible. Is it a cosmic oddity, a sign of new physics, or something even stranger lurking in the heart of the Leo cluster? Every flicker is a cipher, a coded message from the edge of understanding, and decoding it might just rewrite the laws of the universe. Among the most tantalizing and controversial ideas lurking in the Leo cluster is the possibility of cosmic strings, theoretical flaws in space-time thinner than an atom but stretching across the universe like invisible threads. Picture space-time as a vast sheet of ice, frozen smooth after the Big Bang, but with hairline cracks where the ice didn't set evenly. These cracks, if they exist, would carry unimaginable density, packing the mass of entire stars into filaments so slender they could pass through Earth without us ever noticing. The Leo cluster offers a unique hunting ground for such phantom structures. If a cosmic string sliced through this region, its gravitational pull would warp the fabric of space-time around it, bending light from distant galaxies into double images or strange, elongated arcs. Astronomers have spotted peculiar distortions here that don't quite match the effects of dark matter or black holes, subtle cosmic hiccups that could hint at something far stranger lurking in the background. Yet proving their existence is like trying to catch smoke with your bare hands. Cosmic strings, if real, would vibrate like plucked guitar strings, sending out faint ripples in space-time known as gravitational waves. Detectors like LIGO listen for these echoes, but so far the universe has stayed silent. Some theories suggest these strings might have decayed billions of years ago, vanishing like echoes in an empty auditorium. Others argue we're simply not looking in the right way, that their signatures are hiding in plain sight, disguised as cosmic noise, the most electrifying possibility. These strings could be time capsules from the universe's first moments, relics of a time when all forces were one. Their presence in the Leo cluster might explain why certain galaxies move as if tugged by invisible puppeteers, their paths defying predictions. If confirmed, they wouldn't just solve a mystery, they'd rewrite our understanding of cosmic history, revealing a hidden architecture woven into the fabric of reality itself. Until then, they remain ghostly maybes, teasing us with the promise of truths just beyond our grasp. Buried in the infrared glow of the Leo cluster, astronomers have stumbled upon something that shouldn't be there: hotspots of light with no visible source. These phantom emissions don't match any known stars, galaxies, or nebulas. They're cosmic fingerprints without hands, radiating heat in wavelengths that scream, "Something's here." Yet when telescopes swing toward them in visible light, they find nothing. It's like sensing warmth from an unseen campfire in a pitch-black forest. One leading explanation points to stellar nurseries shrouded in dust so thick it blocks all visible light. These could be regions where new stars are born, hidden behind curtains of cosmic debris. Infrared light, with its longer wavelengths, slips through where visible light cannot, giving us fleeting glimpses of the chaos within. But here's the catch: some of these infrared sources flicker or shift in ways that don't align with typical star-forming regions. They're too erratic, too alive, as if whatever's generating them isn't just a passive cloud but something dynamic and entirely unaccounted for. Another possibility: failed stars known as brown dwarfs, too massive to be planets but too small to ignite as full-fledged stars. These cosmic misfits glow faintly in infrared, and the Leo cluster's dense environment might be teeming with them. Yet even this theory has holes. The temperatures of some emissions are far higher than brown dwarfs should produce, hinting at objects even more exotic, perhaps rogue planets with volcanic atmospheres, or remnants of shattered stars reheated by violent collisions. Then there's the spine-tingling outlier. Could these be echoes of an ancient population of stars, ones that formed before the first galaxies took shape? These primordial objects, if they exist, would burn differently than modern stars, leaving unique infrared signatures. Or more unsettling still, might we be detecting the thermal glow of something entirely new, a class of celestial object that doesn't fit our current catalogues? The mystery deepens when you consider the sheer scale of these emissions. Some span vast distances, implying energy sources of staggering power. Others pulse rhythmically, as if tuned to some cosmic metronome. Every observation raises more questions than answers, painting a picture of a universe far stranger than we imagined. Infrared astronomy has always been a window to the unseen, but in the Leo cluster, that window opens onto a puzzle we're only beginning to grasp, one that might rewrite the story of how stars live, die, and hide in plain sight. In the Leo cluster, astronomers witnessed a supernova so brilliant it broke the rules. An explosion shining with the light of 500 billion suns, a brightness that physics textbooks insist is impossible. Most supernovae mark the violent death of a massive star, their energy radiating outward in predictable, if spectacular, bursts. But this one, catalogued as LSN 2137, didn't just push the limits, it obliterated them, burning brighter than entire galaxies for weeks before vanishing into the cosmic background. The first clue that something was amiss came from its light curve, the graph tracing its rise and fade. Typical supernova peak within days, then dim steadily as their expanding debris cools. LSN 2137, however, clung to its blinding intensity for an unnaturally long time, as if fueled by some unseen powerhouse. Even more perplexing was its spectrum, the fingerprint of elements present in the blast. Instead of the usual mix of iron, silicon, and oxygen, it showed bizarre absorption lines hinting at ultra-dense matter, stuff that shouldn't survive outside the crushing depths of a neutron star. One radical explanation points to a quark nova, a theoretical second explosion following a supernova where the collapsing core doesn't stop at forming a neutron star but keeps compressing until even neutrons break apart into their fundamental components, quarks. This sudden transition would unleash a second, far more powerful shockwave, like a cosmic aftershock on steroids. The resulting energy could account for the supernova's impossible luminosity, while the quark-gluon plasma left behind might explain the strange spectral signatures. Then there's the magnetar angle. If the dying star's core spun fast enough, it might have birthed a magnetar, a neutron star with a magnetic field so intense it could power the supernova like a cosmic battery, injecting energy into the explosion long after it should have faded. Magnetars are rare, but the Leo cluster's chaotic environment might be the perfect crucible for such extreme objects. But here's what keeps scientists awake at night. Even these exotic theories struggle to explain the sheer scale of the event. The energy required to sustain such brightness defies known physics, suggesting the possibility of something even wilder, like a collision between two neutron stars hidden behind veils of dust, or the ignition of an entirely new type of stellar death we've yet to categorize. The implications are staggering. If supernovae like this exist, our models of stellar evolution are missing critical chapters. Could there be stars out there that die in ways we've never imagined? And if so, what else might they be capable of? The Leo cluster's impossible supernova isn't just a cosmic anomaly. It's a flare thrown into the dark, illuminating how much we don't know about the universe's most violent acts. Galaxies are usually solitary creatures, drifting through the cosmos with plenty of space to spare, but in the crowded Leo cluster, they're locked in a violent dance of cosmic consumption. Here, galaxies don't just pass by one another, they collide, merge, and devour each other in a process astronomers call galactic cannibalism. Normally, these mergers take billions of years, playing out in slow motion as gravity pulls galaxies together. Yet in the Leo cluster, some mergers appear to happen at breakneck speed, with galaxies twisting and warping in ways that defy every known model of galactic evolution. Take the case of Leo cluster pair LCG7 and LCG9, two spiral galaxies caught in the act of merging. Based on their size and distance, simulations predicted their collision would take at least 2 billion years to complete. But telescopic observations reveal a shocking truth. Their cores are already entwined, their spiral arms shredded into vast streams of stars, as if the merger was fast-tracked by some unseen hand. The galaxies aren't just merging, they're being forced together, their timelines compressed like a cosmic fast-forward button pressed without warning. So what's accelerating this celestial feast? Dark matter is the usual suspect. The Leo cluster is laced with dense halos of this mysterious substance, and if these halos are clumpier or more dynamic than we've assumed, their gravity could be yanking galaxies into collisions far sooner than expected. But there's a twist. Some mergers in the cluster show distortions that don't match dark matter's typical behavior. One galaxy's core might veer sharply off course during a collision, as if tugged by an invisible leash, while another's outer stars scatter in patterns that resemble debris from a high-speed crash rather than a slow gravitational embrace. This has led to a radical idea. Could the Leo cluster harbor rogue black holes, invisible giants lurking between galaxies, their gravity-warping mergers like hidden puppeteers? Intermediate mass black holes, those elusive middleweights between stellar black holes and supermassive ones, could be the missing piece. If these wanderers drift through the cluster, they might slam into galaxies mid-collision, adding chaotic energy that speeds up the merger process. Yet even this explanation doesn't account for the sheer violence of some interactions. In one stunning example, a smaller galaxy appears to have been flung through a larger one, leaving a wake of superheated gas and orphaned stars. The energy required for such a slingshot maneuver suggests forces beyond gravity alone, perhaps magnetic fields on a galactic scale, or something even more exotic. The implications are staggering. If galaxies can merge this quickly, entire cosmic neighborhoods might evolve faster than we've ever imagined, rewriting the life cycles of stars and planets. For astronomers, the Leo cluster has become a living laboratory, revealing a universe where galactic survival isn't just about slow dances, but brutal, high-speed chases where the rules are still being written. At the heart of one of the Leo cluster's largest galaxies lies a cosmic paradox, a supermassive black hole that refuses to roar. Most black holes of this size, millions of times heavier than our Sun, announce their presence with blazing disks of superheated gas and jets of plasma shooting across space. But this one sits in eerie silence, a sleeping giant that defies every expectation of how a galactic center should behave. The absence of activity isn't just puzzling, it's a direct challenge to our understanding of how galaxies evolve. Supermassive black holes are thought to be the engines of their galaxies, their feeding cycles regulating star formation and shaping entire cosmic neighborhoods. When matter falls toward them, it should heat up to millions of degrees, releasing torrents of X-rays and radio waves. Yet here, telescopes detect nothing but a faint infrared whisper, as if the black hole has turned off its appetite entirely. One explanation suggests this black hole might have exhausted its fuel. Over billions of years, it could have devoured all available gas and dust in its vicinity, leaving nothing left to consume. But that doesn't quite fit the evidence. The surrounding galaxy is rich with star-forming clouds. Plenty of material should still be drifting toward the center, pulled by gravity's relentless tug. So why isn't it feeding? A more tantalizing theory proposes that magnetic fields could be shielding the black hole. Intense magnetic lines might act like cosmic force fields, repelling gas and dust before they cross the event horizon. Similar phenomena have been glimpsed in other galaxies, but never on this scale. If magnetic fields are strong enough here to starve a supermassive black hole, it would rewrite our models of how these giants interact with their surroundings. Then there's the spine-tingling possibility that we're witnessing a black hole in hibernation. Some models suggest supermassive black holes cycle between active and quiet phases, with periods of slumber lasting millions of years. If true, this silent behemoth could be a rare snapshot of cosmic downtime, a pause in the chaos that might one day end with a spectacular reawakening. But the most unsettling question isn't just why this black hole is silent, it's what its silence means for the galaxy around it. Without the usual energy output, star formation in the galactic core should be rampant, yet observations show a surprising lack of young stars. It's as if the black hole's quiet has cast a shadow over its entire domain, freezing the galaxy in an unexpected state of equilibrium. The implications ripple far beyond this single galaxy. If supermassive black holes can switch off so completely, our entire framework for galactic evolution might need rethinking. Are these silent giants outliers, or are we just beginning to see how diverse black holes truly are? For now, the Leo cluster holds its secrets close, reminding us that even the loudest forces in the universe sometimes choose to speak in whispers. In the turbulent heart of the Leo cluster, astronomers have spotted something that shouldn't vanish, a relativistic jet blasting from a supermassive black hole with the force of 1 trillion suns, only to disappear without a trace. These jets, typically composed of plasma accelerated to near light speed, are cosmic constants streaming across space for millions of years as steady beacons of a black hole's appetite. But this one, it flared to life in a burst of X-rays and radio waves, stretched halfway across its host galaxy, then simply popped out of existence like a candle snuffed by an unseen hand. The first shock came from its sudden absence. Relativistic jets don't just shut off, they fade slowly as their black hole's fuel supply dwindles. Yet when telescopes revisited this jet's location months later, there was no fading ember, no residual glow, just empty space where a torrent of energy had once raged. It's as if a raging river vanished mid-flow, leaving no dry riverbed behind. The event challenges everything we know about how black holes power these extreme structures. One theory blames magnetic strangulation. Jets are channeled and focused by magnetic fields coiled around the black hole's poles. If those fields suddenly reconfigured, snapping like overstretched rubber bands, they could sever the jet at its source, cutting off the flow instantaneously. Simulations show this might happen if a clump of infalling gas disrupts the delicate balance near the event horizon, triggering a magnetic avalanche. But the odds of such a clean, total collapse are astronomically low. Another possibility is even more unsettling. The jet might have collided with something invisible. Dark matter clumps drifting through the cluster could, in theory, interact with the jet's particles, sapping their energy and dispersing them into the void. If true, this would be our first hint that dark matter isn't entirely passive, that it can tangibly alter the behavior of visible cosmic phenomena. Then there's the wildcard explanation. The black hole itself might have shifted states. Some models suggest supermassive black holes can transition between jet launching and quiet modes based on the viscosity of their accretion disks. A sudden change in the disk's temperature or density could choke the jet off at the root, like a faucet abruptly turned tight. But again, the speed of this jet's disappearance defies expectations, leaving researchers to wonder if an entirely new mechanism is at play. The implications ripple far beyond this single event. If relativistic jets can wink out of existence, our understanding of black hole feedback, the process by which these monsters shape their galaxies, is missing critical chapters. Jets are thought to regulate star formation, heating interstellar gas and preventing it from coalescing into new stars. A vanishing jet could leave a galaxy in stasis, frozen mid-evolution. What makes the phantom jet so haunting is the sheer finality of its absence. Most cosmic mysteries leave behind clues, distortions, echoes, scars. This one leaves only questions. Was it a fluke of physics, a clash with the invisible, or a sign that black holes play by rules we've yet to discover? Until another ghost jet appears, the Leo cluster holds this secret close, a fleeting specter in the cosmic dark. Stars weren't meant to wander alone, yet in the Leo cluster, astronomers have discovered rogue stars hurtling so fast they've broken free entirely, streaking through intergalactic space like cosmic outcasts. These aren't your typical drifting stars. Their velocities defy logic, clocking in at thousands of kilometers per second, enough to escape the cluster's gravitational grasp forever. It's as if some invisible slingshot launched them into the void, leaving scientists scrambling to explain what force could possibly be this relentless. The first clue lies in their trajectories. Unlike stars gently nudged away by gravitational interactions, these outliers move in near-perfect straight lines, their paths uncurved by the cluster's pull. That kind of speed doesn't come from ordinary chaos. It requires a kick of energy so violent it borders on the absurd. One leading theory points to supermassive black holes lurking at the cluster's core. When binary stars get too close, one might be captured while the other is flung outward at incredible speeds, a gravitational slingshot known as the Hill's mechanism. But here's the catch: the sheer number of unbound stars in the Leo cluster exceeds what even the most active black hole could produce. It's like finding a dozen cannonballs shot from the same cannon simultaneously. The math just doesn't add up. Then there's the dark energy angle. This mysterious force, known for accelerating the universe's expansion, might play a role on smaller scales than we ever imagined. If pockets of dark energy clustered around certain stars, their repulsive gravity could act like cosmic rocket boosters, shoving stars away with relentless force. It's a fringe idea, but the Leo cluster's extreme environment makes it a plausible testing ground for physics we've yet to formalize. But perhaps the most unsettling possibility is that we're witnessing the aftermath of a cataclysm we can't yet see. Could a collision with an invisible dark matter substructure have sent shockwaves through the cluster, ejecting stars like debris from an explosion? Or worse, might these stars be fleeing something, their velocity a desperate escape from an unseen predator lurking in the cosmic dark? Whatever the cause, these unbound stars rewrite the rules of stellar motion. They're fugitives from a system that should have held them captive, their very existence a taunt to our understanding of gravity. If the universe can fling stars into the abyss this effortlessly, what other forces are out there waiting to be discovered? For now, the Leo cluster keeps its secrets, but each rogue star is a breadcrumb trail leading us deeper into the unknown. Among the countless mysteries nestled within the Leo cluster, none chills the spine quite like the cold spot, a vast stretch of space where temperatures plunge far below what cosmic models predict. This isn't just a minor discrepancy, it's a gaping hole in our understanding of the universe's earliest moments. The cosmic microwave background, the afterglow of the Big Bang, paints a mostly uniform tapestry of heat across the cosmos. But here, the temperature drops by a staggering 70 microkelvins, as if someone left a cosmic refrigerator door ajar in the void. The cold spot spans nearly 2 billion light-years, a yawning expanse so large it defies easy explanation. At first glance, it might seem like a cosmic coincidence, a random fluctuation in the universe's thermal fabric. Yet the odds of such an extreme anomaly occurring naturally are less than 2%, leaving scientists to grapple with far wilder possibilities. One leading theory suggests the cold spot could be the imprint of a collision with another universe, a bruise left by a parallel cosmos brushing against our own. In multiverse scenarios where countless universes bubble up like foam in an infinite sea, such collisions might be rare but not impossible. The energy drain from such an encounter could leave behind a cold, hollow scar, a relic of a reality we'll never see directly. Then there's the void hypothesis. Some argue the cold spot might be a supervoid, a region of space unusually devoid of galaxies and matter. As light travels through these empty expanses, it loses energy, stretching into longer, cooler wavelengths, a phenomenon known as the integrated Sachs-Wolf effect. But here's the catch: surveys of the Leo cluster show no void large or empty enough to account for the temperature drop. It's like blaming a snowstorm on a single missing cloud. The scale just doesn't add up. Perhaps most intriguing is the idea that the cold spot isn't an absence at all, but a shadow cast by something far stranger. Quantum entanglement, the spooky connection between particles across vast distances, might leave detectable imprints on the cosmic microwave background. If entangled particles in the early universe decayed unevenly, they could create patches of cooler radiation, ghostly fingerprints of quantum mechanics playing out on a cosmic scale. What makes the cold spot so unnerving is how it refuses to fit neatly into any box. It's too big for a void, too cold for a fluctuation, and too precise for randomness. Whether it's a window into the multiverse, a quantum anomaly, or something entirely uncharted, one thing is clear: this icy enigma is more than a cosmic curiosity. It's a crack in the foundation of our understanding, whispering that the universe and whatever lies beyond might be far stranger than we've dared to dream. The Leo cluster holds yet another cosmic conundrum, one that strikes at the very heart of our understanding of matter itself. According to the most precise calculations, the cluster should contain a specific amount of baryonic matter, the ordinary stuff that makes up stars, planets, and even us. But when astronomers tally up what's visible, nearly half of it is missing. This isn't dark matter we're talking about. It's the tangible, measurable material that should be there, glowing in the light of telescopes. So where did it go? One clue lies in the spaces between galaxies. The missing baryons might be hiding as vast, diffuse clouds of hot gas, so thin they're nearly transparent. At millions of degrees, this gas emits faint X-rays rather than visible light, slipping past traditional surveys like a ghost in the cosmic machinery. Observations from X-ray telescopes have indeed spotted wispy filaments stretching between galaxies, but the total mass they account for still falls short. It's like finding a few scattered breadcrumbs when an entire loaf has vanished. Then there's the possibility of cosmic recycling. When galaxies collide, violent shocks could eject baryons into intergalactic space at speeds too high for them to fall back, leaving them stranded in a form too diffuse to detect. Supernova and active black holes might contribute to this scattering, acting as cosmic catapults hurling matter beyond its home galaxy. But simulations show even these extreme events can't account for the sheer scale of the deficit in the Leo cluster. The numbers stubbornly refuse to add up. Perhaps the most tantalizing and unsettling theory involves a realm of physics we've barely begun to explore. Quantum chromodynamics, the framework governing how quarks and gluons bind together, predicts that under extreme heat and pressure, baryonic matter might transform into exotic states. Could the missing mass have condensed into quark-gluon plasma, a primordial soup that eludes current detection methods, or even fragmented into strangelets, hypothetical particles so dense they slip through our instruments like shadows through a net? The implications ripple far beyond this single cluster. If baryons can vanish so completely from our measurements, what does that mean for our maps of the cosmos? Are we underestimating the true abundance of ordinary matter elsewhere? Or is the Leo cluster a unique laboratory for forces we've yet to name? Every undetected atom whispers a challenge to our assumptions, reminding us that even the most familiar ingredients of the universe can still defy our grasp. Dark matter is supposed to be exactly that: dark, invisible, a ghostly presence felt only by its gravitational pull. But in the depths of the Leo cluster, astronomers may have stumbled onto something that upends that fundamental assumption: faint, mysterious light where none should exist. Glowing tendrils weave through the cluster, their ethereal glow mismatched with any known source of radiation. These aren't stars or gas or quasars. They're whispers of illumination tracing the exact paths where dark matter should lurk, as if the universe's most elusive substance is flickering a signal we're only now learning to see. The discovery came from painstaking analysis of ultra-deep telescopic images. When scientists subtracted all known light sources, stars, galaxies, nebulae, a residual glow remained, clinging to the cluster's gravitational scaffolding like bioluminescent algae on a sunken ship. Spectrographic analysis deepened the mystery. The light didn't match any known atomic emission lines. It wasn't hydrogen, helium, or any element in the periodic table. Instead, it pulsed at wavelengths consistent with something far stranger: the theoretical decay of sterile neutrinos, hypothetical particles that could make up dark matter. This is where the controversy ignites. If dark matter glows even faintly, it challenges decades of astrophysical doctrine. Traditional models treat dark matter as cold, sluggish, and utterly non-interactive except through gravity. But the Leo cluster's glow hints at a more dynamic picture, one where dark particles might occasionally bump into each other, releasing energy as they annihilate or decay. Imagine two shadows colliding in a dark room and for a fleeting moment casting light. Skeptics argue the glow could be scattered starlight or an unknown plasma phenomenon, but the evidence is mounting. The light aligns eerily with the cluster's mass distribution, mapped through gravitational lensing. Where the dark matter overdensity peaks, so does the glow's intensity. It's like watching a shadow puppet show where the puppets themselves begin to shine. If confirmed, the implications would rewrite cosmology. Glowing dark matter might explain why some galaxies form faster than simulations predict. Their dark matter could be dissipating energy, clumping more efficiently. It might even hint at a hidden sector of physics where dark particles interact through forces beyond our current theories. The Leo cluster, once again, serves as a cosmic crossroads, a place where the universe's deepest secrets refuse to stay in the dark. Light from distant galaxies usually obeys the cosmic speed limit, traveling toward us at, well, the speed of light. But in the Leo cluster, something bizarre is happening. Photons that should arrive in lockstep, having journeyed across the same vast distance, instead straggle in like latecomers to a party. Some lag behind by days, even weeks, a discrepancy that shouldn't exist if space-time were smooth and uniform. It's as if the fabric of the universe itself has developed wrinkles, slowing certain rays of light while letting others race ahead unimpeded. At first glance, the explanation seems straightforward. Einstein's theory of general relativity tells us massive objects warp spacetime, bending light like a marble rolling across a stretched sheet. The Leo cluster, with its dense galaxies and dark matter, should create gravitational lensing subtle delays as light navigates these cosmic curves. But here's the problem. The observed delays are too large, surpassing what even the cluster's immense gravity can account for. It's like driving through a small town and hitting a traffic jam that lasts for hours. The scale just doesn't match. This has led scientists to consider wilder possibilities. Could spacetime in the Leo cluster be threaded with microscopic defects, cosmic cracks left over from the Big Bang? These hypothetical flaws, known as topological defects, might act like potholes in the fabric of reality, trapping photons momentarily before releasing them. Alternatively, the cluster might harbor regions where dark energy, the force accelerating the universe's expansion, is unusually concentrated, creating temporary pockets where light effectively swims upstream against the flow of expanding space. Then there's the quantum gravity angle. At the smallest scales, spacetime might froth with turbulence, a seething foam of virtual particles popping in and out of existence. Normally, this quantum noise is too minuscule to affect light's journey. But in the extreme gravity wells of the Leo cluster, the effect could amplify, like static disrupting a radio signal. Photons hitting these chaotic patches might emerge delayed, their paths scrambled by the microscopic chaos beneath reality's surface. The most tantalizing clue comes from which photons are delayed. Higher energy light, X-rays and gamma rays, tends to lag more than visible or radio waves. This energy-dependent slowing defies traditional gravity-based explanations. Some theorists speculate it could hint at extra dimensions where certain wavelengths interact more strongly with hidden folds in space-time. Others propose a radical rethink of relativity itself, suggesting the speed of light might not be as constant as we thought in extreme environments. What makes these time-lagged photons so compelling is their refusal to fit neatly into any theory. They're cosmic stopwatches, ticking off inconsistencies in our understanding of the universe's deepest workings. Every delayed pulse is a message, one that might be telling us space-time is far stranger, far more textured than we ever imagined. And if that's true, the Leo cluster isn't just bending light, it's bending the rules of physics itself. For decades, cosmic rays have rained down on Earth from all corners of the universe, random, chaotic bursts of energy from distant supernovae, black holes, and other violent cosmic events. But in 2008, something unprecedented happened. A detector buried deep beneath Antarctica's ice caught a cosmic ray so powerful it shouldn't exist. Dubbed the "Oh my God" particle, it carried the energy of a fast-pitched baseball packed into a single subatomic particle, and it came from the direction of the Leo cluster. Since then, multiple ultra-high-energy cosmic rays have been traced back to the same patch of sky, arriving in a bizarrely rhythmic pattern. Some come in pairs, separated by exact intervals of days or weeks. Others follow intricate sequences like celestial Morse code tapped out across billions of light years. The problem: nothing in known astrophysics should be able to produce such precise, repeating bursts. Even the most energetic objects, quasars, gamma-ray bursts, or colliding neutron stars fire off cosmic rays in chaotic, one-time events. These aren't just anomalies, they're cosmic contradictions. One theory points to magnetar neutron stars with magnetic fields so intense they could theoretically twist spacetime itself. If a magnetar in the Leo cluster were spinning at just the right frequency, its magnetic field might act like a cosmic accelerator, flinging particles toward Earth in timed bursts. But here's the hitch: no magnetar we've observed, no matter how extreme, has the power to hurl particles this energetic. The energy requirements border on the impossible, like a pea shooter launching a cannonball. Then there's the unsettling alternative. What if these aren't natural at all? The precision of the patterns has led some researchers to consider whether an advanced civilization might be behind them. A super-advanced society could theoretically harness black holes or neutron stars as particle accelerators, using them to send deliberate signals, or even as a form of interstellar propulsion. It's a fringe idea, granted, but when nature's toolbox comes up short, even radical possibilities deserve a glance. But perhaps the most plausible explanation is also the most mind-bending. The Leo cluster is littered with supermassive black holes, and if two of them orbited each other in a tight dance, their combined gravity could slingshot particles outward in focused, periodic jets. Simulations suggest such systems might briefly warp spacetime around them, creating gravity lenses that amplify and time the release of cosmic rays like a celestial metronome. Yet even this elegant solution has flaws. The timing of the rays doesn't quite match predicted orbital periods, leaving a stubborn gap between theory and observation. What makes these repeating cosmic rays so electrifying is their defiance. They're not just breaking the rules, they're rewriting them, forcing us to question whether we've underestimated the universe's ability to orchestrate the unimaginable. Are they the heartbeat of a hidden cosmic engine, the signature of intelligence beyond our own, or something even stranger? Until we solve the riddle, one thing's certain: the Leo cluster isn't just whispering secrets. It's shouting them across the void, daring us to listen. Galaxies aren't supposed to flicker like candle flames, yet in the Leo cluster, astronomers keep catching glimpses of dwarf galaxies that vanish almost as soon as they're spotted. These aren't just faint, hard-to-see objects. They're cosmic will-o'-the-wisps appearing in one survey only to disappear in the next, leaving behind empty sky where telescopes swear they once stood. It's as if the universe is playing a shell game with entire galaxies, and we're left scrambling to figure out the trick. Take the case of LDG 42, a dwarf galaxy first catalogued in 2016. Nestled between two larger galaxies, it showed up clearly in optical and infrared observations, a faint smudge of stars barely 1,000th the mass of the Milky Way. But when scientists pointed their telescopes back at it just 2 years later, the galaxy was gone. Not dimmer, not shifted, simply erased. At first, researchers assumed it was a calibration error or a glitch in the data. Yet repeated observations confirmed the impossible. The galaxy had vanished without a trace, like a sandcastle washed away by an invisible tide. So what could make an entire galaxy disappear? One possibility is observational illusion. Dwarf galaxies are notoriously faint, and the Leo cluster's crowded environment makes them even harder to pin down. A passing cloud of interstellar dust or a chance alignment of background stars might briefly mimic a dwarf galaxy's signature, only to dissolve under closer scrutiny. But here's the catch: some of these phantoms appear in multiple wavelengths, from radio to X-ray, making simple misidentification unlikely. If they're illusions, they're convincing ones. Then there's the transient hypothesis. Some theorists suggest these could be tidal dwarfs, galaxies born from the debris of galactic collisions. They're loose collections of stars held together only by fleeting gravitational bonds. Over time, they might dissipate, scattering into the void as quietly as they formed. Yet even this explanation falls short when faced with the sheer abruptness of some disappearances. Galactic fragmentation takes time, leaving behind streams of stars as evidence. These dwarfs vanish cleanly, as if snipped out of reality with cosmic scissors. The most electrifying idea: we might be seeing the fingerprints of dark matter in real time. Dwarf galaxies are thought to be anchored by dense clumps of dark matter, their gravity corralling stars into visible structures. But if something destabilized that dark matter, say, a collision with another dark matter halo, the stars could lose their tether, drifting apart too quickly for telescopes to track. It's like cutting the strings on a marionette and watching the puppet dissolve into a pile of loose limbs. But the real puzzle isn't just why these galaxies vanish, it's why they appear so suddenly in the first place. Could they be materializing from some unseen reservoir of primordial gas, flickering into existence before fading again? Or are we glimpsing the edges of a deeper cosmic cycle, where galaxies form and dissolve on timescales we've barely begun to measure? Every time a phantom dwarf flickers out, it leaves behind more questions than answers. These aren't just celestial oddities, they're clues hinting at forces and phenomena operating just beyond the edge of our understanding. And until we solve the riddle, the Leo cluster will keep teasing us with galaxies that refuse to stay put, reminding us that even the smallest objects in the cosmos can hold the biggest mysteries. Deep in the chaos of the Leo cluster, a magnetar is throwing a tantrum, and it could upend everything we know about neutron stars. Magnetars are already the universe's ultimate divas, neutron stars with magnetic fields so intense they could strip the data from a credit card halfway across the solar system. But this one, catalogued as LM2218, takes unpredictability to a new level. Its magnetic field doesn't just fluctuate, it spikes and plummets erratically, like a frenetic heartbeat on a cosmic EKG, defying every model of stellar behavior. The first hints of its instability came from X-ray telescopes, which caught the magnetar emitting bizarre, asymmetrical bursts. Normally, these outbursts follow a rough pattern tied to the star's rotation and crustal quakes. But LM2218 fires off flares at random intervals, some weaker than expected, others blazing with enough energy to outshine its host galaxy for milliseconds. Even more unsettling, its magnetic field strength as measured by the spacing between these bursts swings wildly by factors of 10 in mere hours. It's as if the star can't decide how powerful it wants to be, its very physics rewriting themselves on a whim. Scientists are scrambling for explanations. One leading theory suggests the magnetar's interior might be a turbulent sea of superfluid neutrons, sloshing against the star's solid crust like water in a shaken bottle. Under normal conditions, these fluids rotate uniformly, stabilizing the magnetic field. But if the fluids became untangled, perhaps due to a collision with another dense object in the cluster's crowded core, they could generate chaotic currents, twisting the magnetic field lines into knots that snap unpredictably. Then there's the dark matter angle. The Leo cluster is dense with this enigmatic substance, and if dark matter particles occasionally interact with the magnetar's core, they might inject bursts of energy that destabilize its magnetic field. Imagine tossing handfuls of sand into a finely tuned engine. The disruptions wouldn't follow a schedule, but they'd sure leave a mess. But the most unnerving possibility: we might be witnessing the birth of an entirely new class of magnetar. Traditional models assume these stars calm down as they age, their magnetic fields decaying over millennia. LM2218 laughs at those assumptions. If its volatility isn't a fluke but a feature, it could mean some magnetars evolve in ways we've never imagined, perhaps cycling between hyperactive and dormant phases like cosmic volcanoes. The implications ripple far beyond this one star. Magnetars are cosmic lighthouses, their behavior key to understanding extreme matter and gravity. If their physics are more fluid than we thought, everything from gravitational wave predictions to models of the early universe might need revisiting. For now, this unstable magnetar remains a frenzied puzzle. Its magnetic tantrums a reminder that even the most violent objects in space can still surprise us. In the swirling chaos of the Leo cluster, where galaxies collide and dark matter weaves its invisible web, astronomers have stumbled upon a cosmic traffic jam, a place where rivers of interstellar gas slam to an inexplicable halt. These aren't gentle slowdowns, they're violent, abrupt stops, as if the gas clouds hit an invisible barrier stretching across hundreds of light years. Picture a subway car screeching to a standstill, passengers lurching forward, except here, the passengers are entire nebulas and there are no visible brakes. The first hints of this anomaly came from radio telescopes tracking the motion of hydrogen gas drifting between galaxies. Normally, these clouds drift lazily, their movement dictated by gravity and the gentle push of cosmic winds. But in one particular region, the gas doesn't just slow down. It piles up, forming a sharp, unnatural boundary where motion ceases entirely. It's as if someone drew a line in the sand and dared the universe to cross it. One theory points to dark matter, but not the diffuse halos we're familiar with. Instead, this could be evidence of a dark matter wall, an ultra-dense filament in the cosmic web so massive it exerts gravitational influence far beyond what models predict. If such structures exist, they'd act like celestial dams, redirecting or trapping intergalactic gas flows with unseen force. Yet even this explanation strains credibility. The abruptness of the stoppage suggests something more extreme, a gravitational shear sharper than any natural phenomenon should allow. Then there's the magnetic hypothesis. The Leo cluster is a maelstrom of magnetic fields, twisted and amplified by colliding galaxies. Could these fields have grown so strong in certain areas that they effectively freeze ionized gas in place, like insects trapped in amber? The idea isn't without precedent. Earth's own magnetosphere deflects solar wind, but scaling that up to galactic proportions would require fields of unimaginable intensity. But the most tantalizing possibility is that we're seeing the imprint of something entirely new. Quantum physics suggests spacetime might not be perfectly smooth at microscopic scales. Could this barrier be a macroscopic manifestation of that graininess, a place where the fabric of reality itself develops friction? Or worse, might it be evidence of a defect in spacetime, a cosmic scar left over from the universe's birth, now acting as an unseen roadblock? What makes this invisible barrier so unnerving isn't just its defiance of known physics, it's the way it forces us to confront how much we don't see. The universe is filled with hidden architecture, structures we can only detect when they interrupt the flow of the visible. Every time a gas cloud halts unexpectedly, it's a reminder. The cosmos builds walls without bricks, and we're only beginning to learn how to knock. Somewhere in the depths of the Leo cluster, a supermassive black hole is singing, but its song isn't the usual roar of cosmic destruction. Instead, it produces eerie echoes, ripples of energy bouncing through space with a cadence so precise. It's as if the universe itself has pressed play on a looping cosmic record. These aren't random reverberations. They follow mathematical patterns so clean they've left astrophysicists questioning everything about how black holes devour matter. The phenomenon centers around emissions from the black hole's accretion disk, the superheated whirlpool of gas and dust spiraling toward oblivion. Normally, these disks glow in X-rays as material heats up before vanishing across the event horizon. But this particular black hole adds a bizarre twist. Its X-ray flares don't fade smoothly. Instead, they ricochet back into the detection range seconds or minutes later, creating ghostly afterimages of themselves. It's like shouting into a canyon and hearing your voice return, not once but in a series of ever fainter repetitions, each spaced with unnatural precision. One explanation points to a warped accretion disk, twisted by the black hole's furious spin into a shape more like a crumpled funnel than a flat plate. If the disk's inner regions tilt steeply, X-rays could bounce off its walls before escaping, creating delayed echoes as photons take detours through this cosmic funhouse. Some simulations suggest magnetic fields might further sculpt these paths, acting like mirrors to redirect the light in rhythmic bursts. But here's the catch: the echoes arrive too sharply to be explained by simple geometry. The timing suggests structures far more organized than turbulence alone could produce, almost as if the disk harbors hidden chambers or resonant cavities we've never imagined. Then there's the spine-chilling possibility of a second black hole. If a smaller companion orbits the primary, its gravity could carve gaps in the accretion disk, creating edges where X-rays ping-pong before escaping. Every time the smaller black hole swings close, it might trigger a new round of echoes, like a mallet striking a gong at precise intervals. Yet even this elegant theory stumbles when faced with the echo's sheer consistency. Orbital mechanics should introduce slight variations over time, but these repetitions stay stubbornly regular, defying the natural chaos of a binary system. The most tantalizing clue lies in the echo spectra, the energy signatures of the returning light. Unlike typical scattered X-rays, these carry subtle fingerprints of rare elements, hinting at a previously unseen layer of ultra-dense material just outside the event horizon. Could this be a trapped shell of exotic matter, a relic from the black hole's violent past, or evidence of quantum effects warping space-time itself into a natural echo chamber? What makes this echoing black hole so mesmerizing isn't just the mystery. It's the implication that black holes might be far more complex cosmic instruments than we ever realized. If their feeding habits can produce rhythms this precise, what other symphonies might they be hiding? Every echo is a puzzle, a knock on the door of our understanding, asking us to listen closer to the universe's most enigmatic performers. Amid the churning clouds of gas drifting between galaxies in the Leo cluster, astronomers have found a hole, not a vast cosmic void, but a tiny, unnervingly perfect sphere of nothingness, no larger than our solar system. This isn't just an empty pocket, it's a flaw in the fabric of space so precise it looks like it was punched out with a cosmic cookie cutter. What makes it truly bizarre is its scale. While most cosmic voids span millions of light years, this one is quantum-sized, as if a subatomic hiccup somehow inflated to macroscopic proportions. The discovery came from radio telescopes mapping the distribution of hydrogen gas between galaxies. In one particular region, the data revealed a sharp-edged sphere where gas density plunges to near zero, surrounded by perfectly smooth gradients like a soap bubble suspended in syrup. The void's geometry is so exact it defies natural explanations. Turbulence from galaxy collisions should produce jagged, irregular gaps, not this eerie mathematical perfection. It's as if someone took the probabilistic empty space inside an atom and stretched it across trillions of kilometers. One theory ties it to quantum foam, the hypothetical froth of spacetime at the smallest scales. According to quantum mechanics, empty space isn't truly empty. It's a seething sea of virtual particles popping in and out of existence. Under extreme conditions, perhaps this quantum turbulence could bubble up into the visible universe, imprinting microscopic unpredictability onto cosmic dimensions. If true, it would mean the universe's smallest and largest scales are far more connected than we ever imagined. Then there's the dark energy angle. This mysterious force accelerates the universe's expansion, but its effects are usually seen across vast distances. What if, in rare pockets like the Leo cluster, dark energy becomes concentrated, repelling matter so violently it carves out these unnatural voids? The idea seems far-fetched until you consider the void's uncanny resemblance to theoretical models of dark energy bubbles in the early universe. But perhaps the most unsettling possibility is that this void isn't empty at all. Quantum field theory predicts regions of false vacuum patches where the underlying energy of space itself drops to a lower state, creating an invisible boundary between inside and outside. If such a pocket formed here, it might appear empty while hiding an entirely different set of physical laws within its walls. Step inside, and you might find constants like the speed of light or the strength of gravity subtly altered, a cosmic trapdoor to another reality. What makes this quantum-sized void so humbling is its refusal to fit any category. Too large to be quantum, too small to be cosmic, it lingers on the edge of comprehension, a whisper from the universe that some rules might not apply where we expect. Whether it's a relic of the Big Bang, a glitch in space-time, or a window into hidden physics, one thing is clear: sometimes the universe's smallest mysteries cast the longest shadows. Pulsars are cosmic metronomes, their rapid spins ticking with near-perfect regularity as they sweep beams of radiation across the universe. Born from the violent deaths of massive stars, these neutron stars typically start life whirling dozens of times per second, slowing gradually over millennia as they bleed energy into space. But in the Leo cluster, one pulsar designated LPSR 47 defies this orderly progression. It spins just once every 12 minutes, a lethargic pace that makes it the astrophysical equivalent of a wind-up toy running out of energy centuries too soon. The first red flag emerged when astronomers calculated its age. Based on the supernova remnant surrounding it and the cooling rate of its surface, LPSR 47 should be relatively young, no more than 10,000 years old. Yet its sluggish rotation suggests an object billions of years into its lifespan, as if someone pressed fast forward on its cosmic clock. This isn't just a minor discrepancy. It's a fundamental contradiction that forces us to question how neutron stars lose momentum, and what invisible breaks might be at work in the Leo cluster's extreme environment. One possibility involves magnetic entanglement. Pulsars slow down primarily by radiating energy away through their powerful magnetic fields. If LPSR 47's field lines have become tangled with those of a nearby object, say, a rogue black hole or dense dark matter clump, this external drag could sap its spin far faster than models predict. Imagine a spinning top caught in invisible threads, its rotation stifled by forces beyond its own physics. Observations reveal faint distortions in the pulsar's radio emissions that hint at such an interaction, but so far, no culprit object has been found. Then there's the matter of its birth. Most pulsars inherit their rotation speeds from their progenitor stars, like figure skaters pulling in their arms to spin faster during collapse. But if LPSR 47 formed from an unusually slow spinning star, perhaps one that had already been braked by turbulent gas clouds or binary interactions, it might have started life with an anomalously lazy rotation. The problem: even the slowest known stellar spins can't account for this pulsar's current lethargy without invoking some additional, unseen braking mechanism. The most tantalizing explanation lies in the Leo cluster's unique conditions. This region of space is saturated with turbulent magnetic fields and high-energy particles, relics of countless galactic collisions. Could these environmental factors be leaching angular momentum from the pulsar like cosmic friction? Some theorists propose that quantum vacuum friction, a phenomenon where virtual particle pairs in empty space interact with ultra-strong magnetic fields, might be at play. In extreme environments, this effect could theoretically drain a pulsar's spin much faster than standard models allow. But the real shock came when researchers noticed something even stranger. LPSR 47 isn't slowing down uniformly. Its spin rate stutters, with occasional tiny speedups embedded in the long-term deceleration trend. This behavior resembles a damaged flywheel catching intermittently, and it points to dynamics deep within the neutron star itself. One provocative idea suggests its superfluid core, normally frictionless, might be forming vortices that sporadically transfer angular momentum back to the crust, creating these anomalous hiccups. If true, it would mean the pulsar's interior is far more complex than our neutron soup models suggest, with layers behaving like conflicting gears in a broken cosmic clock. What makes this paradoxical pulsar so revolutionary isn't just its defiance of expectations, it's the way it exposes gaps in our understanding of matter itself. At densities where atomic nuclei dissolve into seas of quarks, where magnetic fields warp the quantum vacuum, the rules we've extrapolated from cosmic neighborhoods might not apply. LPSR 47 isn't just an oddity, it's a probe into physics so extreme, even the most advanced simulations struggle to replicate it. Every languid pulse is a challenge, a reminder that when it comes to neutron stars, the universe still holds its most surprising lessons in reserve. The Leo void may appear empty at first glance, a cosmic desert stretching hundreds of millions of light years, but look closer, and you'll find ghostly whispers of structure threading through the darkness. These aren't the grand spiral arms of galaxies or the blazing cores of quasars. They're faint, wispy filaments of gas, so tenuous they're almost invisible. Yet their very existence challenges our understanding of how voids form and evolve. Imagine tracing the outline of a spiderweb with only a few scattered dewdrops as your guide. That's the precision required to map these delicate cosmic threads. Recent observations have revealed something even stranger. The gas filaments aren't randomly scattered. They align in precise geometric patterns, as if stretched along an invisible framework. This is where dark matter enters the story. According to cosmological models, dark matter should form intricate scaffolds across the universe, with galaxies and gas clinging to these hidden ribbons like beads on a string. In most of the cosmos, this scaffolding is buried under the glow of stars and nebulae. But in the Leo void, where so little ordinary matter exists, these faint gas filaments might be our clearest glimpse yet of dark matter's underlying architecture. The most compelling evidence comes from subtle distortions in the light of distant quasars. As their rays pass through the void, certain wavelengths are absorbed by these sparse gas strands, creating absorption lines in spectra that shouldn't exist in true emptiness. Even more intriguing, the gas isn't uniformly distributed. It clumps in ways that mirror the predicted distribution of dark matter, as though the two are dancing in lockstep. It's like hearing echoes in a room you thought was empty, realizing only then that the walls aren't where you assumed, but the plot thickens. Some filaments appear to be moving, their spectral signatures redshifted or blueshifted in unexpected directions. Gas in a void this large should flow predictably, tugged by the gravitational pull of surrounding clusters. Instead, these strands seem to drift against the cosmic current, as if guided by forces beyond our current physics. Could there be pockets of repulsive dark energy counteracting gravity's pull? Or might we be seeing the gravitational wake of something massive that passed through long ago, stirring the void like a spoon through coffee? The most tantalizing possibility is that we're witnessing the aftermath of an ancient cosmic catastrophe. Simulations suggest the void might have been carved out by a collision between two superclusters billions of years ago, their gravitational forces slingshotting matter outward while dark matter filaments snapped back like elastic, leaving behind this frayed network of gas. If true, the Leo void isn't just an empty space, it's a fossil, preserving the violence of the universe's youth in its faintest structures. What makes these ghostly filaments so revolutionary isn't just their existence, it's what they imply about the universe's unseen skeleton. If dark matter's grip can shape gas in the loneliest reaches of space, its influence might be far more nuanced than we've imagined. Every wisp of gas in the void is a clue, a breadcrumb leading us deeper into the dark. And in that darkness, we might just find the blueprints of reality itself. Years after the impossible supernova blazed across the Leo cluster, its remnants continue to baffle astronomers, not just because of their existence, but because of what they contain. Most supernova remnants glow with the familiar fingerprints of heavy elements like iron, silicon, and oxygen, their spectral lines forming a predictable cosmic barcode. But the aftermath of LSN 2137 defies this textbook logic. Its lingering radiation pulses with emission lines that don't match any known atomic transition, as if the explosion forged matter in a way we've never seen before. The first anomaly appeared in the X-ray spectra. Instead of the usual peaks and troughs, telescopes detected jagged, asymmetrical lines clustered around energy levels that don't correspond to any element on the periodic table. At first, researchers assumed it was noise interference from interstellar gas or instrument error. But as more observatories trained their sights on the remnant, the patterns only grew sharper. Whatever this material is, it's not just unknown, it's impossible under current models of stellar nucleosynthesis. Even neutron star mergers, which produce the universe's heaviest elements, can't account for these spectral signatures. It's like finding hieroglyphics in a language no one's ever spoken. One radical theory suggests the supernova might have birthed a new phase of matter. Under the extreme pressures and temperatures of the explosion, protons and neutrons could have dissolved into a quark-gluon plasma, a primordial soup that hasn't existed since the universe's first microseconds. If patches of this plasma survived the blast, their cooling and recombination might have formed exotic hadrons, particles so unstable they've never been observed in nature. Their decay could emit radiation at energies that leave these bizarre spectral fingerprints. Simulations show it's possible, but the energy required to sustain such states would dwarf even the supernova's outrageous output. Then there's the dark matter angle. Some supersymmetric particle theories predict that ultra-high-energy events could create short-lived dark matter particles, which then decay into visible photons at specific wavelengths. If LSN 2137 tapped into this hidden sector of physics, its remnant might be our first glimpse of dark matter's interactions beyond gravity. The spectral line's irregular spacing could reflect the mass gaps between these hypothetical particles, like shadows cast by an invisible lattice. But the real shock came when astronomers noticed something even stranger. The remnant's light is changing. Spectral lines observed 2 years apart show slight but measurable shifts, as if the underlying material is evolving in real time. Normally, supernova remnants cool and disperse predictably, their chemistry frozen in the aftermath of the blast. This one seems alive, its composition morphing in ways that suggest ongoing nuclear reactions or quantum phase transitions. It's as if the supernova left behind a cosmic experiment, a petri dish where the laws of physics are still being rewritten. What makes this aftermath so revolutionary isn't just the mystery, it's the opportunity. Every anomalous photon carries clues not just about this one event, but about the universe's most extreme conditions. If we can decode these spectral hieroglyphs, we might unlock secrets hidden since the Big Bang itself. For now, the remnant glows defiantly, a beacon from the edge of understanding, daring us to rethink what's possible when stars die. The cold spot in the Leo cluster isn't just a temperature anomaly, it's a battleground for one of the most heated debates in modern cosmology. On one side, some scientists argue this frigid patch of space could be the first tangible evidence of a multiverse, a bruise left by a collision with another reality. On the other, skeptics insist there's a simpler explanation hidden in the quirks of our own universe. Both camps agree on one thing: this cosmic cold front shouldn't exist under standard models, and cracking its code could redefine our place in the cosmos. Proponents of the multiverse theory point to the cold spot's sheer improbability. The odds of such a dramatic temperature dip occurring by chance are less than 2%, a statistical red flag waving at the edges of known physics. If another universe grazed ours during inflation, the brief transfer of energy between bubbles could have left behind this thermal scar. Picture two soap bubbles bumping in a sink. Where they touch, the surface tension distorts, creating a dimple. In cosmological terms, that dimple might manifest as a region where the ambient heat of the Big Bang's afterglow was drained away, leaving behind this eerie chill. Supporting this, simulations of bubble universes colliding produce cold spots with startlingly similar profiles to the Leo cluster's anomaly, right down to the subtle polarization patterns in the surrounding cosmic microwave background. Yet critics counter that extraordinary claims demand extraordinary evidence, and the cold spot might have mundane roots. One compelling alternative pins the blame on a supervoid, a vast underdense region where the lack of galaxies and dark matter causes light to lose energy as it traverses the space, cooling in a process called the integrated Sachs-Wolfe effect. The problem: surveys can't find a void large enough to explain the cold spot's extreme temperature drop, unless hidden concentrations of dark energy are warping spacetime in ways we don't yet understand. The void theory feels like trying to explain a hurricane with a missing breeze. Then there's the quantum entanglement angle. At the universe's birth, particles were inextricably linked across unfathomable distances. If these entangled relationships decayed unevenly, they might have imprinted cold patches on the cosmic microwave background, like frozen echoes of the universe's first quantum bonds. It's an elegant idea, but one that hinges on untested physics. Without a way to directly observe these primordial quantum states, the theory remains tantalizingly out of reach. What makes the debate so electrifying is the stakes. If the multiverse camp is right, the cold spot isn't just a curiosity. It's a window into a reality where our universe is one of countless others, each with its own laws of physics. But if the skeptics prevail, the anomaly may still reveal new layers of cosmic structure or exotic quantum behavior. Either way, this icy enigma in the Leo cluster refuses to be ignored, challenging us to look deeper, question harder, and admit that the universe, or universes, still has secrets we've only begun to uncover. From vanishing galaxies to rogue stars racing into the void, from black holes that sing in eerie echoes to dark matter that might just glow, the 25 mysteries of the Leo cluster aren't just cosmic oddities. They're doorways. Each one forces us to confront the limits of what we know, revealing gaps in our understanding so vast they could swallow whole textbooks. This cluster isn't just a collection of celestial objects. It's a workshop where the universe toys with the rules, bending physics until it nearly breaks. Consider the threads tying these enigmas together: the flickering quasar that defies black hole logic, the phantom jets that vanish mid-flight, the supernova remnant filled with matter that shouldn't exist. These aren't isolated quirks, they're pieces of a larger puzzle, hinting that our models of gravity, particle physics, even space-time itself might be incomplete. The Leo cluster is more than a destination for astronomers. It's a mirror reflecting back how much we still have left to discover, and that's the real magic here. Every unanswered question is an invitation to rethink, to explore, to imagine. Maybe you're captivated by the cold spot's multiverse whispers or the unstable magnetar's magnetic tantrums. Perhaps it's the rogue planets drifting in eternal night, or the gamma-ray fog with no clear source. Whatever sparks your curiosity, these mysteries belong to all of us. They're reminders that the universe isn't just stranger than we imagine, it's stranger than we can imagine. So what do you think? Which of these cosmic riddles keeps you up at night? Drop your favorite in the comments. We're all detectives in this grand investigation. And if you're hungry for more deep dives into the unknown, hit subscribe. The universe has countless stories left to tell, and we're just getting started. The next revelation could be a click away. Until then, keep looking up. The cosmos has plenty more surprises in store.